Hi everyone! Over the past few days we've been studying various topics related to applications of the derivative. Today we'll see another one, and this one is called linearization. Now, you might recall that the big ideas of calculus that we've been studying have been rates of change and how they relate to each other. Particularly we saw that with optimization and related rates, but we've also seen that with the derivative in general as an instantaneous rate of change. We also saw it with a secant line, which represents the average rate of change. Today, we're going to focus on linear functions. We like linear functions a lot because we know pretty much everything there is to know about lines. And so one really cool property about very nice functions, which we'll call smooth functions, is that smooth functions look like lines if you zoom in really close. So we call this property local linearity. A smooth function looks linear in a very small area, a local area. So today, we're going to explore this a bit more. What this really means is that the tangent line, which we know how to find already, is a good approximation for a function if you're pretty close to the point of tangency. So let's explore that a bit. First, let's recall how we find the tangent line. So to find a tangent line, what we do is we know that the derivative represents the slope of the tangent line. So we can use this to figure out what the equation of the tangent line should be. Let's say we're at some particular point, a, f of a. Then the tangent line can have the following equation. F of x minus f of a, that's our y minus y1, should equal the slope, which is f prime of a, times x minus a. This is just point slope form that we've seen for a little while now. And then if we were to solve this for f of x, we'd get something that looks like f of x is f of a plus f prime of a times x minus a. This is our formula for linearization. Linearization really just means find a line that approximates the function. Well, here's our line that approximates the function. Occasionally, instead of f of x, you'll see this written as L of x, because f is probably our function, L is the linearization of that function. So that's the notation that we're going to use. And we'll see in a moment why this is particularly helpful for us for approximations. So perhaps in the past, you've seen some functions that you know certain values of, but maybe you don't know other values of and would like to. Some examples that jump to the top of my mind are trigonometric functions and also radical functions. So let's look at one of each of those. First, I'm going to rewrite the formula that we have here. So the linearization of x is going to be f of a plus f prime of a times x minus a. This is the linearization of x at the point A, or near the point A. So here's a typical question that you might see in a linearization section. Approximate the value of sine of 0.1. Chucks. Now, here's what I'm thinking. Oh, sine of 0.1, that's probably pretty close to sine of 0. And I know sine of 0 is just 0, right? So let's start by sketching this. Now, obviously we have this formula and we can just go right to it, but it's good to sketch so that we have a good understanding of what's going on here, and we can check our answers using more than one method. So here's a sine curve, here's what it looks like. And sine of 0.01 maybe is right about there, really quite close to the origin. We'd expect a pretty small number, pretty close to 0. Let's sketch in the tangent line here. Here's my tangent line. Great, there's my tangent line. Okay, so I can see this line and see see what I'll get out for my linearization and then make sure that these match up well so that my intuition matches my actual calculation. If I get something weird like, oh, the tangent line should have a negative slope, then I know I've done something wrong because pictorially I can see that it has to have a positive slope. Great. So my first goal is I want to pick a value for a. Now you might be tempted to say, oh, a is just 0.01. Now if a is 0.01 though, we're going to have a problem because we don't know the value of sine 0.01. So using 0.1 to approximate it is going to give us the same issue. We don't know that value, so how can we use that value? F of a is the very first thing. If I did sine of 0.1 here, then already I don't know what it is. So I'll need to pick an a value that's pretty close to 0.1, but that I know the y value of. So here I'm going to pick a is 0. And this will be nice because I know sine of 0. So let's see here. My L of x should be f of 0, which is sine 0, plus, oops, let me just move this over, f prime of 0, well, the derivative of sine is cosine of 0 times x minus 0. Sine of 0 we recall is just 0, cosine of 0 we recall is 1. That means the linearization here is just x. What this means is that whenever we are near the point 0, sine of x looks almost identical to the line y equals x. This is really, really, really interesting, and it's related to something that we saw earlier. You might recall that we've seen that the limit as x goes to 0 of sine x over x is 1, and this gives us further support for that statement, saying that, hey, sine and x look pretty much exactly the same near 0, so when you divide them near 0, you should get 1. Makes a lot of good sense. Okay, but again, right, we need to recall what the question is asking. It's asking us to approximate the value of sine 0.1, and to do that, we'll use our linearization model, and we'll plug in the value 0.1, and we'll get out 0.1. So our conclusion here is that sine of 0.1 is very nearly 0.1. That's our approximation. Great. I'll just let that settle in for a moment, and then I'll move on to another example. But you should be able to notice that this line here looks pretty similar to y equals x, and is also tangent here, so everything seems to check out for us. We were expecting an answer pretty close to 0, and we got an answer pretty close to 0. Again, good stuff. So now I'm going to change the question a bit. We can continue doing more examples with trig, but if you understand the process, you should be okay for other examples that you try on your own. We're going to use the same linearization model, and instead of approximating a trig function, let's approximate a radical function. So let's approximate the cube root of 220. Whew. Now let's see here. Maybe I remember what a cube root function looks like, maybe I don't, but I remember that a cubic function looks like that. Now a cube root function should be the inverse of this guy, so it would be reflected over the line y equals x. So our cube root function should look like this. And you could confirm this for yourself, either on your calculator or by picking your favorite perfect cubes, plotting them, and connecting the dots. So this is our function y equals the cube root of x, and somewhere over here is the point. X is 220. Now the first goal, again, is to find a nice nearby value where we definitely know the cube root of it. In this case, you may recall that 216 is equal to 6 cubed. 216 is pretty close to 220, so that'll be our best a value. If you weren't sure about that, what I'd suggest doing is testing out the perfect cubes. 1 cubed is 1, 2 cubed is 8, so on and so forth. We get 5 cubed is 125, 6 cubed is 216, and 7 cubed is 343. So we can see that the best cube there is 216. So we're going to set our a value equal to 216. Okay. And now I'll just linearization it up. Here we go. The f of a is now the cube root of 216. The cube root of 216 is 6 plus f prime of a. Oh, okay. So here's the deal. Our function here is the cube root of x, right? So our function, we recall f of x, is the cube root of x. So if we want to find its derivative, we turn the cube root into an exponent. F of x is x to the 1/3 power. And then we'll just use the power rule. F prime of x is 1/3 x to the negative 2/3. Great. So that's going to be our value here. It's going to be 1/3 times 216 to the negative 2/3. And then, of course, times x minus a, x minus 216. Great. So L of x should be 6 plus, all right, we know that 216 to the 1/3 is 6, because the cube root of 216 is 6. So 216 to the 2/3 is just 6 squared, which is 36. And the negative exponent, remember, makes it the reciprocal. So it turns that 36 into 1/36. We then multiply that by 1/3, and we get 1 over 108. And that'll be times x minus 216. Now, this is the equation of our tangent line. And so what always helps me is to kind of sketch the tangent line here at this point that we're given over here. Remember, the tangent line in this particular case we found was at 216, not at 220. So very close, but not quite. And then the tangent line looks something like that. Now, if you look at that tangent line, it's very nearly horizontal, which is good because we got this slope of 1 over 108. So a very, very small but positive slope that seems to match what we think here. So that's good news for us, seems reasonable. And now remember, we're trying to approximate the cube root of 220, so we'll just go ahead and plug in 220 for x. So L of 220 is going to be 6 plus 1 over 108 times 220 minus 216. And that'll give us, this is 4. 4 over 108 is 1/27th. So you should get L of 220 is 6 and 1/27th, or 6.037 repeating. Okay. Now again, we should check this. The cube root of 220, we know that that should be pretty close to 6, and our approximation is also pretty close to 6. That's some good stuff. That's some really good stuff. You could use your calculator to check what the actual cube root of 220 is, and then see how far off we were with our linearization model. Okay. There is one last thing that I want to talk about today. And that's going to be functions of the form 1 plus x to the power of k. Now this is a binomial being raised to some power, so we might call it a binomial expansion. And our linearization model is going to approximate this polynomial. This is particularly nice because then you can extend it. You could change this from a 1 to a 2 to a 3 to a 4 to whatever. You could change the coefficient in front of your x. You could do lots and lots and lots of cool things, but anytime you have some polynomial of this form, we can rewrite it approximately as a straight line. And here's what I'll do. I'll just go right to my formula, and what I'm going to do in particular is I'm going to choose my a to be 0. Don't worry too much about why I'm choosing a to be 0, other than the fact that 0 happens to be the nicest number, so I'll just pick it to be 0. So if a is 0, then I can come up with this nice form here. L of x should be, well, f of a, plug in 0 here, I get 1 to some power. That's just always 1. Okay, f prime of a. All right, well, let's see here. F prime of a, I'll bring down the k out in front. So this will be k times 1 plus 0 to the k minus 1. And then, of course, times x minus 0. And now 1 to some power is, again, always 1. So this means my linearization is 1 plus kx. And that's it. That's my linearization formula. You can use nifty things like this to approximate entire families of functions, right? This is a family of functions here. And so if this happened to be 1 plus x quantity squared, I know that looks pretty much like 1 plus 2x if I'm close to 0. If this happened to be 1 plus x quantity cubed, that would look pretty much like 1 plus 3x as long as I'm close to 0. This fact is actually a building block for a deeper topic called Taylor series that we won't cover in this course. But what a Taylor series does is it continues on. Rather than just finding a linear term, it additionally finds a quadratic term and a cubic term and so on and so forth, and comes up with this nice formula to relate every single smooth function to a polynomial. And polynomials, while not quite as great as linear functions, 1, will give better approximations, and 2, are pretty much as nice as linear functions in the sense that we know lots about them. So that's our video on linearization. Hopefully it helps you with a practice problem that you're going to do, and please come to class tomorrow with any questions. All right, see you later.